Okay, so what I was just saying to my students off video or off camera a few seconds ago is I said, look, just because you have an absorbance or just because you have an alkene doesn't necessarily mean you're going to get this absorbance here at 31 reciprocal centimeters. Just because you have an alkyne doesn't mean you're going to get that absorbance at 3,300. Let me explain why. Right? What if you had a tetrasubstituted alkene? This is an alkene, but there's no sp2 hybridized carbon-hydrogen bonds, and so you're going to have no signal at 3,100 reciprocal centimeters. What if you have a disubstituted alkyne? Well, you've got no sp hybridized carbon-hydrogen bond, and so you're not going to see that. So just because you don't have this at 3,100, just because you don't have a signal at 3,300, doesn't necessarily mean that you don't have an alkene or an alkyne, respectively. And so when it comes to spectroscopy, what you're going to find is that you've really got to take a 30,000 foot view. You know, when you're doing spectroscopy, you've got to look at all of the facts before you start making judgments. What else? Excuse me. Resonance delocalization has an effect on bond strength. Yeah, it does. Okay. It says here that resonance delocalization affects the strength of a covalent bond. And therefore, if it affects the strength of the bond, it's going to affect your F. Therefore, it's going to affect what? Your wave number. So if you look at just a ketone, right? If you look at the carbonyl stretch in a ketone, it's usually around 1720 reciprocal centimeters. But if you have what's called a conjugated ketone, now let me explain what conjugated means. Conjugated means that the bonds alternate double, single, double, single, right? That's what a conjugated system is. So it's like you have a pi bond, then a sigma bond, then a pi bond, then a sigma bond, then a pi, right? And it just keeps going like this. So this is what we call a conjugated ketone because here we have a pi bond, then we have a sigma bond, then we have a pi bond, right? They're alternating like that. And you see that that carbonyl doesn't absorb at 1720. It absorbs at a lower wave number. If it absorbs at a lower wave number, what does that mean? Since wave number is directly proportional to bond strength, that means that if this is a lower wave number, that the bond must be weaker. Now, why would that be weaker? Well, the good news is that we can answer that based off of what we learned in chapter 2 when we talked about resonance or delocalization of electrons. We know that for the ketone, there's only one resonance contributor that we can draw here. We know that this one is the best resonance contributor because everything has a complete octet here. But anyhow, if we look at the conjugated ketone, we see that we can draw one additional resonance structure that is at the bottom right of the slide here. And what that means is that this bond, okay, which put another way, this carbonyl has more single bond character than this carbonyl does. If the one that I have circled in blue has more single bond character, what does that mean? It means it's weaker. If it's weaker, what does that mean? It means its F is a lower value. If the F is a lower value, what does that mean? It means it's going to absorb at a lower wave number. Nothing more than that. So if you have a conjugated ketone or a conjugated ester or something of that ilk, if you have conjugation, again, what does that mean? It just means you have a pi bond. Oops. If you have a pi bond, then a sigma bond, then a pi bond, right? It weakens that bond, and then you're going to get an absorption at a lower number. So if you're like wondering, okay, what's the take-home message? Like, how would I use this? What does this mean for me as a student who's just trying to get a good grade in organic chemistry? What this means is that if you memorize, let's say, that a ketone absorbs around 1720, and you saw a strong absorbance just below 1720, it might be a clue that you've got a conjugation or a conjugated ketone, right? It's just, you kind of put the pieces together, right? The infrared spectrum isn't like a photo. It's not like a photograph that you can just look at it and say, hey, that's Jim. That's my friend George or something like that. No, you have to look at the evidence and then you have to evaluate that. Well, what about the intensity? Remember I told you that you had strong signals, right? We had strong, we had weak, and then somewhere in the middle, we had, medium intensity in terms of our signal. Well, the reason why we have strong and weak signals actually has to do with bond polarity. So it says here that when a bond undergoes a stretching vibration, its dipole moment also oscillates. And when the dipole moment oscillates, what it does is it creates like a little electric field. Now that electric field that is created acts kind of like an antenna in its ability to pick up the infrared electromagnetic radiation, or to absorb, I should say, the infrared electromagnetic radiation. So what's the take-home message? Is that the greater bond polarity you have, or the stronger the dipole you have, this more infrared light it's going to absorb. So again, like that's why I use the word antenna, right? If you think about the longer antenna you have, well, the more signals you can pick up. Well, if your bond is more polar, it's going to act like an antenna, and it's going to pick up more infrared, electromagnetic radiation. So it's going to have a stronger absorbance. Okay, nothing more than that. So if you compare these two signals here, you would say, this one probably has a stronger dipole, okay, because it's absorbing more electromagnetic radiation than this one here. Is it absorbing some? Sure, yeah, but not nearly as much. So it's not going to have a strong dipole. So what's something that's got a dipole in it that shows up all the time in organic chemistry in functional groups? A carbonyl. Carbonyls are present in what? Ketones, aldehydes, esters, carboxylic acids, amides, other functional groups that we haven't looked at yet, things like called carbamates, for example. So when you see that strong absorbance in that 1700 reciprocal centimeters region, it probably means that you have a carbonyl in your compound, okay? Whereas if you look at the absorbance of an alkene, right, a carbon-carbon double bond, well, that's not going to have nearly as strong a dipole, right, because the two carbon atoms have the same electronegativity. And an alkene actually absorbs, or the carbon-carbon double bond stretches around 1630. So it's around 1630 reciprocal centimeters, whereas the carbonyl in a ketone, let's say, will absorb around 1715. We'll put around 1715. But we're not talking about the wave number right now. We're talking about the absorbance. And since this has a stronger dipole, it's going to absorb more electromagnetic radiation. Therefore, it's going to have a stronger absorbance than something like the carbon-carbon double bond. And that's it, my friends. Okay. But there's so many traps that you can fall into in organic chemistry. And a couple of semesters ago, I had a guy in my lab who loved to joke around, and he was a very good student. And he said, what's organic chemistry? Memorizing a lot of rules and then all the exceptions to those rules. So here's an exception. Let's say you had an alkene, and I just told you, and I'm actually going to give you a table for your next quiz that tells you that the carbon-carbon double bond of an alkene is going to absorb around 1630 reciprocal centimeters. Well, this is an alkene. This is 2,3-dimethyl 2-butene. That's the name of the molecule. But I don't see a signal at 1630. Why wouldn't it be? Right? Because since it's completely symmetrical, there's no dipole. Right? We'll put here no dipole at all. So again, you've got to be careful in spectroscopy. Okay, you got to be very careful when you weigh out the evidence. All right. Anyhow, now I also told you that this signal shape could be broad, or it could be sharp or narrow. Okay, now why would it be narrow in some cases and broad in others? Well, what you really need to know in organic chemistry 1 is that usually when you have a broad signal, most of the time it's because you've got an oxygen bound to a hydrogen. Okay, most of the time. You could say the same thing about nitrogen-hydrogen bonds a little bit, like to a lesser degree, but usually you're dealing with some kind of oxygen-hydrogen stretch. Now, where do you find oxygens and hydrogens bound to each other by a single bond? You find them in alcohols, right? And you also find them in a carboxylic acid, okay? We have an oxygen-hydrogen stretch here in an alcohol or a carboxylic acid. So let's talk about why they would be broad like that. And you can probably guess that it's got something to do with hydrogen bonds. Yeah, so you know that an alcohol, let's say, or an oxygen-hydrogen bond will hydrogen bond if it can, okay? Now, what does hydrogen bonding do? And I know that everybody here has studied hydrogen bonding, not only in chapter 1 of this class, but you would have studied it in general chemistry 1. But what happens is when the lone pair on one oxygen, let's say, interacts or forms that hydrogen bond with the partial positive charge on a hydrogen, what it does is it kind of yanks on the oxygen-hydrogen bond, right? It kind of pulls it away a little bit here. See how that bond is stretched? So what's that going to do? That's going to weaken it. What's that going to mean? It means it's going to absorb a lower frequency of electromagnetic radiation, right? Because the bond is weakened. You're affecting the force constant. But hold on, what if the hydrogen bond is even further away and the effect is less? Well, then it's going to stretch it, but not as much. What if it's closer, right? So what you end up doing is, since the hydrogen bonds are transient, the sample is going to contain a whole bunch of oxygen-hydrogen bonds, but they're going to have a whole bunch of variations in bond strengths. What does that mean? It means it's going to absorb a range of electromagnetic radiation, so it's going to have a broader signal, right? Because you have this whole range of wave numbers that are going to absorb. Because why? Because wave number is proportional to force constant, but the bond keeps weakening and stretching and getting compressed and all this, okay? Now, can you have a narrow peak for an oxygen-hydrogen stretch? Yeah, you can, okay? If you had a sample that's really, really, really dilute so that there's no hydrogen bonding, then you would see a sharp signal. Let me show you what that looks like. It is possible that if you have an alcohol that's maybe like kind of dilute and kind of not dilute, you might get some of the oxygen-hydrogen stretch that is a result from an oxygen-hydrogen that is not hydrogen bonded to anything. And so you get some free hydroxyl, and then you get the one that's participating in hydrogen bonding. Look, I'll level with you guys. This might be worth the value of one multiple choice question on your next quiz, and I will not ask you about the free hydroxyl on your final exam, okay? I'll just level with you right now. 99% of the oxygen-hydrogen bonds you're going to see in this class and in the lab with Mr. Geiger would be broad, okay? It's just the concepts that we want you to know, right? We want you to understand. If you understand why this broad peak, broad absorption occurs, then you should understand why, if there's no hydrogen bonding, why it would produce a narrow signal. Nothing more than that, okay? That's kind of what we're getting at here in this class. Now, if you have a carboxylic acid, you guys know what a carboxylic acid is, right? If we draw a carboxylic acid like this, what's cool about carboxylic acids is that they can do this kind of thing where they form like a dimer. Put around a little bit here just to make it a little nicer. So they can form this kind of dimer. What the heck's a dimer? Okay. A dimer means that you've got an opportunity for a hydrogen bond donor and a hydrogen bond acceptor that does this kind of thing where they, the functional group can participate in donation and accepting both at the same time. And so it causes like mega stretching of the oxygen hydrogen bond. And so out of all the functional groups that we're going to look at in this class, the easiest one, and I don't like to use the word easy, but the easiest one for students to detect is the carboxylic acid. Why? Because the stretch range is so humongous, okay? The oxygen-hydrogen stretch usually is in the range of 3,300. So where's 3,300? That's around here to 2,400. So it's so big. Whenever you see a giant thing, and if you're like, man, this takes up like the whole spectrum. Yeah, it kind of does. That means that you've got an oxygen-hydrogen stretch from a carboxylic acid. What else is in a carboxylic acid? There's a carbonyl. So you also see that stretch from the carboxylic acid carbonyl around what? 1,700, right? This is 1,700 right there. So already we're starting to get a feel for how to interpret an infrared spectrum. Now, before we move on, I want to talk about another thing here. And that is, something like my students are all, when you teach organic chemistry, you teach great students, okay? I have really good students who are really good thinkers. All of you are very good thinkers. And I'll usually have somebody whose brain is just going a mile a minute and they're thinking and they're like, Mr. Dion, what about all this crud over here? Now hold the phone. Remember, I told you that was the fingerprint region. We weren't going to spend a lot of time down there. The reason why is because most of the information, not all, but most of the information that we're going to need in Chemistry 3101 can be garnered from the diagnostic region, 1,500 reciprocal centimeters and above. Okay, so that's why we're kind of ignoring this right now. It doesn't mean it's not important, but it's not as important for this class. So there you go. There's the dimer drawn there, but anyhow, you get the idea there. All right. So what about a primary and a secondary amine? If you're wondering what the difference between a primary amine, A primary amine is one where the nitrogen has two hydrogens attached to it, like this. And a secondary amine is one where the nitrogen only has one hydrogen attached to it in two R groups like that. That's a primary and secondary amine. They both have nitrogen-hydrogen stretching signals. Here we have two in the primary and we have only one in the secondary. Because nitrogen-hydrogen bonds are capable of hydrogen bonding, they're also going to give you a broadened absorption. Primary amines give you two signals. So we see two absorbances for primary amines, and it's not a result of each of them giving a different signal, each nitrogen-hydrogen bond. It's because they can do symmetric and asymmetric stretching, whereas the secondary amines only show you one signal. So again, for the primary, we see two signals or two absorbances, whatever you want to call it. And here we only see one signal. Okay. Now the whole idea between symmetric and asymmetric stretching, good gravy. I hate doing this, but let me turn off my slides here for a second. Turn on my camera. Okay. So symmetric and asymmetric stretching. Okay. So you've got a nitrogen. Let me back up in my office here again. I don't know if you can see me, but you got an amine. There's two bonds. You got, here's the nitrogen. There's two nitrogen-hydrogen bonds. Right. If you've got a secondary amine, you've only got one nitrogen-hydrogen bond. It can only stretch one way. You get one absorbance. Okay, one signal for a secondary amine. When you have a primary, you've got two nitrogen-hydrogen bonds. What the book is saying and what my slide is saying, it's saying there's not one absorbance for one of them and then one for the other. There's two types of stretching. There's symmetric stretching. This gives you one of the signals, okay, symmetric. And then there's asymmetric, and that's what gives you the other signal. Okay, so symmetric stretching and asymmetric stretching. So this is one of the signals. This is the other signal. It's got nothing to do with one from this one and one from that one, which I don't know why the book places so much emphasis on that, but hey, you know, Dr. Klein knows more than me about how to teach or how to explain things in organic chemistry. He's been doing it for longer than me, so we'll go with him. All right, there we go. So here's a primary amine. So this is the primary amine. Primary amine. And this is the secondary amine. Secondary amine. What do you notice? The signals are kind of broad, okay? But they're not as broad as the oxygen-hydrogen stretch. Why? Because the hydrogen bonding isn't as strong between nitrogen and hydrogen as it is between oxygen and hydrogen. What else do you notice? I noticed that the signals are not nearly as strong, right? They're weaker, right? They have about a medium absorbance or maybe even weak. Why is that? It's because the dipole, right? Remember the antenna for picking up the electromagnetic radiation, right? The dipole between a nitrogen-hydrogen bond is weaker than the one between an oxygen-hydrogen bond. The one between an oxygen-hydrogen bond is quite a bit stronger. All right, there you have it. What else? So what do you do when you're given an infrared spectrum? And that's what we're gonna take a look at some in a few minutes here. There's a table 14.2 in your textbook. It says it summarizes some of the key signals that help us identify functional groups present in a molecule. And we're going to look at a version of that table in a few seconds here. So often the molecular structure can be identified from an infrared spectrum. The first thing that I always do when I'm handed an infrared spectrum, and I'm actually kind of misspeaking because I'm usually the first guy to go for the lowest hanging fruit, but whatever. What you should do is draw a line around 1,500 reciprocal centimeters. Between 16 and 1850, you look for double bonds, maybe a carbon-carbon double bond, maybe a carbon-nitrogen double bond, maybe a carbonyl, right? You look for those. Then between 21 and 2300, you look for triple bonds, either a triple bond between carbon and carbon or a triple bond between carbon and nitrogen. Then above 2700 all the way to 4000, you look for oxygen-hydrogen bonds or nitrogen-hydrogen, so NH bonds, CH bonds, oxygen-hydrogen bonds, okay? Then you look at the wave number, intensity, shape, and you try to decide, you know, what kind of functional group might I have? All right, so it's really handy to do this whole thing where you draw a line like that, and then you can get some information from that. All right. So I'm going to stop recording here just for a second because